This video is about torque, but specifically when torque is not receiving a 90-degree force. Okay, so that angle in our torque equation is the angle between R and F. So the angle between the radius of whatever is turning and the force. So let's look at a couple examples, and let's see if we can't pick out our angles. All right, so up here we have 3 angles. Which one is correct? Well, the blue is the thing that's turning, the blue line. So if we look up here, on the one on the left, you see you have the blue line, okay, and then the force. Well, there's your angle. However, if you think about it, here's the blue line, here's the force. That's also your angle. But that works because sine of 60 and sine of 120 is exactly the same. Now, if we look at the one on the right, this 40 degrees is not in between the R and the F. So that's not the correct angle. So we would have to say 50 degrees. And that would have to be sine of 50. You could technically also use cosine of 40, but you're probably less likely to remember to do that, to switch the sine to the cosine. All right, let's look at an example. A door seen below produces a torque, and they want to know which of the forces would produce the least amount of torque. Now, the more perpendicular the force, the greater the torque. Okay, so we look up here and we say, okay, if we're looking for the least torque, we're looking for the least perpendicular. Well, that would be E. Now, we're not done, though, because torque is equal to FR sine theta. Now, with E, that would be sine of 0, which is just 0. So E has a torque of 0. But if we look up here, A also has a torque of 0. Why does A have a torque of 0? Because R is 0. Oops. Okay, so that gives us a torque of 0. So actually both A and E have the least amount of torque equally. All right, so here I have an example of torque about point O, and we want to make one that's equal around point X. Now, with this kind of problem, usually it would be a multiple choice, and there would be, examples and options that you could choose from. But I took the multiple choice out, and I'm just going to kind of work my way through it. All right, so torque is equal to FR sine theta. So in this case, that's 3F. My R is equal to L, and that would be sine of, now is it sine of 30? Here's my R, here's my F. This is the 30 degree, so we're going to have to look at 60. Okay, so that is 3FL, and sine of 60 is 0.866, or the square root of 3 over 2. Okay. Now, if I want to create a torque over here that's equal to that, this video we're going to look at torque when the angle isn't 90 degrees. Now we have our full torque equation. Torque is equal to FR sine theta. Theta is the angle between R and F. Now let's look at some examples so we can visualize and get it in our head. Now I have 3 angles up here, and we want to figure out which is the correct angle. Well, the first angle up here we have is 60 degrees. Now my R, the thing that's rotating, is there, and the force is there. So 60 is the angle between. So 60 is a good angle. Now if we look at the 120, I have my R, I have my F. 120 is the angle in between. Now why can it be both? Because sine of 60 equals sine of 20. Or sorry, excuse me, sine of 120. So both of those are true. Now, if we look at the picture on the right, the 40 degrees, well, here's my R, here's my F. 40 degrees is not in there. So what we have to do is go down and say, okay, this angle would be 50 degrees because that's a 90. So then our theta would equal 50. Okay. Nothing too bad. We just have to be able to visualize it. Now here's a question. There's a door and it has hinges, and you can kind of see where the hinges are, like right there. Okay, and they want to know which force produces the smallest torque. Now, there are three things that affect torque. The size of the force. Now, all these are feeling the same force, so that's not a variable. R and the angle. So how far are you away from the hinges and what your angle is. Now, if I look at A here, the force is right at the hinges, which means my R would be equal to 0, which means my torque is equal to 0. So that's smallest. Now, is there anything else down here that's small? Well, E is also small because sine of 0 is 0. So that also has a torque of 0. So both A and E are equally small as 0. All right, so we'll go with the door again down here, and I apply a certain torque. Now my force is equal to 3F, the length of the door is L, and the angle is theta. Now that's the angle right here. Okay, so let's look at this. Torque is equal to FR sine theta. Now my force is 3F, my R is L. Now sine theta, that angle has to be between R and F. This 30 degrees is not. So we look over here and we get 60. So that would be sine of 60. So if I was to simplify this down, we can have 3FL, and sine of 60 is square root of 3 over 2, also known as 0.866. Now if I was going to do something similar, have a similar torque over here, there are many options I could do. I could change the angle and things like that. I'm going to keep the angle the same just because it'll make life a little bit easier. Okay. Now, if I want that to stay the same, that means this section right here has to equal 3FL. Okay, so let's say I cut my L in half and I apply a force right here. So then I have L over 2. What do I need to do to have the same torque? Well, if I halved my L, I have to double my torque, my force. So 6FL is the same thing as 3FL. So those two are now the same, okay? Nothing too bad, so I apply a force of 6F at a location of L over 2. So if I half my radius, I have to double the force. Whee! All right, here's a nice fun example, and we're going to go through our steps to solve it. So I have a 5-meter long beam. It weighs 300 newtons. So the beam itself has a force of gravity of 300. It's attached to the wall, free to rotate around the pin. The beam is supported by a cable, makes 53 degrees. That's our good angle. And if a person weighing 600 newtons stands 1.5 meters. So 600 newtons, 1.5 meters. Okay, and that 300 newton beam, if it's 5 meters, that center of mass is at 2.5. So we can get all that done. And they want to know the tension in the cable. I'm going to call that tension T. All right, so we located our pivot point. It's right here. We've located all our forces and their R's. Now the R of T is going to be equal to 5. Now we need to sum up our torques. So torque is equal to sum of FR sine theta. Now positive direction is the counterclockwise. So that would be the tension in this case. So I've got tension with an R of 5 and then sine of 53. Now things going counterclockwise, I'm going to subtract, and then I have the 600 person with an R of 1.5 and no angle, or an angle of 90. And then I have the 300 person with an R of 2.5, sine of 90, which is 1. Okay, so this beam is not rotating, which means that whole thing equals 0. And then we just start to solve. Sine of 53 is 0.8, so that's 4t minus 750 minus 900 equals 0, which means 4t is equal to 1650. So t, the tension, is equal to 412.5 Newton meters. Okay? Nothing too bad there. All right. So that gives us the tension in the cable. Now they want to know what forces is being exerted on the wall. Now that kind of makes some sense, right? Because the wall is going to exert a force. It's not going to exert a torque because it's right there at the pivot point, but it does exert a force. If we want to find that force, we need to do step 4, which is sum of the forces. Now I'm going to start with sum of forces in the x direction. All right, so what's acting in the x direction? Well, tension is pulling partly in the x direction, and the wall is pushing in the x direction. So sum of forces in the x is the force of the wall in the x minus the part of tension that's in the x, which is the cosine part. And since it's not accelerating, it equals 0. I got to plug in my t for tension, 412. Cosine of 53, I get FWX is equal to 247.5 newtons. I do the same thing for the y direction. The y direction is a little bit more complicated because there's a lot more forces. Part of tension is pulling up. The sine part of tension is pulling up. Okay? We've got the beam pulling down. We've got the person pushing down. And we have the wall. Now, we don't know whether the wall is positive or negative. I'm going to make him positive. Okay? And that's going to be force of wall on the y. And it all equals 0 again. We plug in our 412.5 for t, and we get our force on the wall in the y is equal to 570.6 newtons. Okay? And that's going to be in the upward direction since the downward is larger. And if we want to find the total force on the wall, that's a squared plus b squared equals c squared. So that means that's the square root of FWY squared plus FWX. Okay, and that's just Pythagorean theorem because we've got a triangle force. You know, one going this way, the other going this way, and we are finding the hypotenuse, which is equal to 621.93 newtons. Bam. Nothing too bad. Just got to make sure you know what to do. And that's what that step 4 is for, to help remind you what you need to do. All right, here's another example. I've got this beautiful wheel. It's a vertical wheel, and it's in static equilibrium. And we want to find the value of m, so value of this guy, in terms of big M, this guy and this guy. Okay, here's my pivot point. I've got forces acting this way, and this way. They're all a distance r. Okay, and the force is equal to mg because it's force of gravity. And then we sum up our torques. Okay, so counterclockwise forces, I've got little mg times r plus, now I've got this big mg, a distance r, but it's not at 90 degrees, right? This angle right here is 60. The angle between the force and the radius, excuse me, would be 30 minus 3 mg r. Okay, there are my torques. Now all we got to do is say, well, that whole thing equals 0. All right, and simplify down. Sine of 30 is 0.5, so I got 0.5 mgr minus 3 mgr and little mgr equals 0. All right, g's and everything is going to cancel out. R's and everything, it's going to cancel out. And we're going to end up with m is equal to 2.5, big M. All right, last one. I have a uniform plank of length 2, mass of 29.5, supported by 3 ropes. We want to find the tension in each rope. All right, now here's the thing. You're finding 3 things. That means we're going to be using 3 equations. 3 unknowns, 3 equations. It's one of those things you got to do. So we pick our pivot point first. That's number 1. I'm going to make this right here my pivot point, because when we do sum of torques, it's going to knock out 2 forces. Okay. Next, identify my forces. I've got my T's. I've got this person right here. I've got the mass of the plank, which is 29.5 times, I'm going to do 10 instead of 9.8. Okay, this person right here is 725. And I've got this force right here. Okay, and that's a fine angle right there at 40. All right, then I do some of my torques. So torque is equal to, well, let's look at this. T2 and T3 are both at R equals 0, so those don't get torques, which means in the counterclockwise direction, I have T1 times R, which is 2, times sine of 40. In the counterclockwise direction, I have 295, because that's this force right here, and 725. And all that equals 0. Okay, and I can solve for T1. T1 is equal to 571. Okay, just solve it out, simplify it down. All right, so I got one of mine. Now I need to find the other ones. Well, we can't do it with torque, so what we're going to do is we're going to do it with our sum of our forces. So I'm going to do sum of forces in the x direction. Sum of forces in the x direction is equal to, well, T1 is acting at an angle, so we know that's going to be in the x direction. So that's going to be T1. The x part is the cosine of 40, because that's the adjacent side to the angle. And the other force acting in the x direction is T3. And all that equals 0. Now we already know that T1 is 571 times cosine of 40 is going to equal T3. So T3 is going to be equal to 437 newtons. Okay? Then we have sum of forces in the y. Okay, so we've done torque, we've done sum of forces in the x, now we have to do sum of forces in the y. Sum of forces in the y is going to be a little bit more tricky because there's more forces. But let's look at what's acting up. T2 is acting up completely. T1 is acting partially up. It's the sine part that's acting up. And then acting down, I have the person, and I have the beam. Okay, I can plug in T1 as 571. All that's going to equal 0. So then I can find out that T2 is equal to 647 newtons. And look at that. 3 unknowns, 3 equations, bim, bam, boom, beautiful. And it's done. All right, that's the end of the lesson. Good luck on your homework.